In this video, we introduce Splatterplots, a novel presentation of point data that enables visualizations that scale beyond traditional scatter plots by explicitly dealing with overdraw. Scatterplots are a common and intuitive way to display point data. However, as the points become closer together, overdraw occurs, causing the display to become indecipherable. Instead, Splatterplots abstract point data using screen space constraints, showing dense regions as smooth shapes while limiting screen space density of remaining points. By enforcing screen space bounds on contour smoothness and display density of points, Splatterplots bound the screen space visual complexity. Zooming in reveals abstracted information as it becomes available, while zooming out increases abstraction. Displaying dense regions as filled-in contours allows us to compare several data subgroups at once. We begin by explaining the steps used to create Splatterplots using a synthetic dataset with a Gaussian distribution. First, we compute a density function from the underlying data points. Threshold and contouring create smooth contours around dense regions. The remaining outlier points are then sampled to reduce clutter. The density of outlier points and amount of density smoothing are controlled by screen space parameters and remain constant during panning and zoom. Zooming in reveals details hidden at higher levels. We also allow the user to interactively change thresholding level, the amount of smoothing, and the density of outlier points. We can show multiple dataset subgroups at once. The color of overlapping regions is computed using LAB color blending. We attenuate the lightness and chroma to emphasize regions with overlap. Here we have one of the synthetic datasets that we use for our performance and clutter experiments. This is a dataset of 3 million points separated into 6 different groups. In the Splatterplot, we can clearly see how the groups relate to each other, clustering in a ring around the 0 point. This is much harder to see in a scatterplot due to extensive overdraw. Abstraction parameters remain constant as we zoom in. This bounds the screen space complexity, revealing points gradually and keeping the contours around dense regions smooth. This is the tree cover type dataset from the UCI KDD repository. This is a dataset of tree cover types from the Roosevelt National Forest of Northern Colorado. Here we show 4 out of the 7 different kinds of cover types, represented in over 500,000 data points. We show 10 different cartographic normalized variables. Even with a large number of data points and subgroups, our visualization enables us to make visual judgments of the data. For example, suppose we wish to discover what is different about aspen and cottonwood, which are the smallest groups in the dataset, versus lodgepole and spruce, which are the largest groups. Notice how the elevation variable tends to separate the kinds of cover types cleanly. Let's take a closer look at the elevation versus horizontal hydrology plot. Here we can see the separation more cleanly. Aspen and cottonwood tend to cluster at lower elevations than lodgepole and spruce. Also, notice how both spruce and lodgepole are more spread out than the other 2 groups, both in the elevation and the hydrology variables. We can also take a look at the vertical hydrology versus elevation plot. Here we see a similar pattern. However, notice how the groups are a lot more clustered in the vertical dimension, especially aspen and cottonwood. Looking at the sparse region, we can clearly see that although the dense parts of the data for lodgepole and spruce follow a similar pattern, they are much more spread out than the other 2 groups. Let's take a look at the vertical versus horizontal hydrology plot. Here we can see that cottonwood especially clusters close to 0 in both dimensions. We can also see that aspen is less spread out than lodgepole or spruce. This becomes even more clear if we change the threshold parameter to include most of the data. Aspen and cottonwood tend to cluster closer to zero in both dimensions, while both lodgepole and spruce are a lot more spread out. This means that both aspen and cottonwood trees grow closer to water sources than the other two groups. Through the use of this green space abstraction and interaction, Splatterplots enables exploration of massive datasets. Thank you for watching.